Today I'll tell you how to use sunflowers to prove non-adaptive data structure load bonds, and this is joint work with Anup Rao. Okay, so let's get started. So so the question that we're interested in is like designing data structures that maintain subsets of numbers from 1 through n, and you want the data structure to support insertions and also median computation and predecessor computation. Okay, so these are the operations that we're interested in, and that we would like to understand what the optimal data structure is for like supporting these operations. Okay, good. So for the rest of the talk, the universe is the set of numbers from 1 through n, and just as a reminder, a predecessor of x is nothing but the largest element in your set that's at most x. Okay, for example, in the set S here, the predecessor of 15 is 13. Okay, good. So the plan for the talk is first show some upper bounds that solves this problem, and also discuss the time complexities, and then formally define what the model is, then discuss our results and show a proof. Okay, good. So one basic data structure that you can use to solve this problem is just have a sorted array along with the size of the set, and here insertions are expensive, they can take time n, but the median computation is very quick, and the predecessor computations take log n time. Okay, and another way to represent your set is just by writing down the indicator vector of a set. In this case, the insertions are very quick, but median and predecessor computations are expensive. Okay, and another data structure, simple data structure that you can think of is the predecessor array, essentially an array of length n, where the ith entry stores the predecessor of I. And here the predecessor computations are very fast, but insertions and medians are expensive. Okay, so here you kind of like see gap in the sense like one of the operations is very expensive, the other one's very quick. So the natural thing to try, or like for such problems, is the binary search tree data structure. So here you can do all these operations in order log n time. So let me just describe what the data structure is. So you have a balanced binary tree of depth log n, and you have n leaves, and each leaf is associated with an element in the universe. And the leaf being empty says the element is not present. If it's not empty, the element is present. Okay, and every internal node stores the number of elements in the left subtree and the number of elements in the right subtree, along with the maximum of the left subtree and the maximum of the right subtree. The small note, someone recently pointed out that like this is slightly different from the usual binary search trees that you might have seen, where like there are no empty leaves usually associated. But I'm like writing it this way for some reason that will be clear soon. Okay, so for example, if you'd like to perform an insertion, you just go to the leaf that corresponds to the element 5 here, for example, and then just walk up to the root and make sure, change all the cells entries to make sure the invariant is satisfied. Okay, and here it's again easy to see that you can do median in log n time, because you go to the root and then you recurse on the left or right depending on the number of elements on the left subtree and the right subtree. Okay, and again, so if you'd like to do the predecessor computation, you go to the leaf that corresponds to the predecessor that you want to compute, and then walk up to the root and find the node that's closest to the leaf which has a non-empty left subtree. And in this case, it's this particular node which has like 13, and you just output the maximum in that left subtree. Okay, and clearly all these operations require order log n time. Okay, and next question to ask is, are log n best, or can you do any better? So there's this very nice data structure due to Van de Bois that actually solves, or performs all these operations in order log n time. Okay, and the key here, I'm not going to discuss the data structure in detail, but the key is, in the case of binary search trees, at every step we divided the universe into like 2 equal halves, but here you're going to like divide it into square root n consecutive intervals, and then recursions at some level. Okay, and just that wouldn't work, and you'll need an auxiliary structure on the side, but roughly that intuition should be good enough. And here the depth of such a tree would be like log n, which gives the log n runtime. Okay, good. Great. So we've seen like a bunch of data structures. So let me formally define the model that we work with. It's the cell probe model that we saw in the previous talk, introduced by Yao So the data structure is nothing but a collection of cells in memory that stores your data, and it usually comes with two algorithms. One is the update algorithm and the other one is the query algorithm. So update algorithms typically bring about changes to your, or make changes to your data, and in our case like insertions are like an update operation. And you can think of like what the data structure does, or the algorithm does, is reads a sequence of cells and makes changes to them. And the time, or the update time, is defined to be the number of cells that are accessed while performing the update or while performing the insertion. Okay. Similarly, you can talk about query algorithms, which typically compute a function of the data that you have. And in this case, you can think of median computation, which is a query. And you again like read a sequence of cells and then output the answer. And the time again here is the number of cells that are accessed, while outputting the answer. Okay. So hopefully that's clear. So before we discuss past work and our results, I'll define the notion of what non-adaptive inserts or like operations mean. So let me define it with respect to insertions here. So an insertion is non-adaptive if the locations of all the cells that are accessed while performing the insertion just depends on the number that's being inserted and does not depend on the contents of the cells that it reads in the process. In the case of the binary search tree that we saw, like once you know that you're going to insert 5, you know that you're going to read only the cells that are associated with the nodes on the path from the leaf corresponding to 5 to the root. So this is clearly non-adaptive. Okay, and the case of median was actually adaptive because you had to make a decision of whether to go recurse on the left subtree or the right subtree depending on the number of nodes that you had, a number of like elements on the left subtree and the right subtree. And predecessors again were non-adaptive here. Okay. Good. And the Van der Waals data structure that I described, both operations are actually adaptive. Okay. Great. So before I actually discuss our results, I just wanted to say that this problem, or the question of proving dynamic data structure lower bounds have been well studied, starting from the work of Redmond Sachs, where they show a lower bound of the form log n over log log n on the maximum of the time to perform the query, or like compute the query or perform the update. Okay, and as Casper mentioned in the open problems session on Monday, the best known lower bound that we have is log n over log log n the whole square, and that's the state of art for dynamic data structure lower bounds. Okay, and in the case of non-adaptive dynamic data structures, we know actually polynomial lower bounds on multiple interesting problems like directed graph reachability and so on. And this was done by Joshua and Casper. Okay, good. So now let me go ahead and discuss our results. So the first problem we consider is like data structures that allow deletions and compute the minimum. In this case, when the deletions and the minimum computations are non-adaptive, then you can show that the time to perform the deletions plus the time to compute the minimum is at least log n over log log n. Okay. So in the case of median, we show that when both operations, both insertions and the median computation is non-adaptive, you can show a lower bound of log n over log log n on the sum of the time for insertions and the time for median computation. Okay, and for non-adaptive insertions, so we actually, in fact, we prove something stronger. So assuming that only the insertions are non-adaptive, you can show that the time to compute the median is at least n to the power 1 over the time to compute or to perform the insertions. Okay. In the case when both operations are actually adaptive, it's actually open to prove even a super constant lower bound. But I have to also remark that I have worst case times in mind when I say this, because there are data structures that performs insertions and computes the median in amortized order one time. Okay. Okay. So for the predecessor such problem, an independent work of Boninger, Brody, and Kephart, they showed that the following trade-off, where either when both insertions and predecessor computations are non-adaptive, you have that either the time to insert is at least log n, or the time to compute the predecessors is like log n or log n. Okay, and in this work we show something stronger, assuming that only the predecessor computations are non-adaptive. You can show that either the time to compute the predecessor is log n or log n, or the time for insertions is at least n to the 1 over the time to compute the predecessors. Okay, and in the case of adaptive inserts and predecessor computations, this is a well understood problem, and we know that the Van der Waals data structure is tight due to a long list of works that consider this problem. Okay, so probably this is a good time to take questions. Any questions on the results? Okay, so just I forgot about this. So just to compare where these parameters lie. In the width vector case, we saw that the insertions being constant time, you have that the median computations were linear. So this gives you a polynomial lower bound on the time to compute the median when the insertions are in constant time. Okay, and in the case of predecessor arrays, when the predecessor computations are constant time, you have a linear upper bound, and the lower bound says you're polynomial when you have constant time to compute the predecessors. And the binary search trees corresponds to a setting where both the predecessor computation and the insertions were log n or log n. Okay, and this is the Van der Waals structure.
Just a quick
Yeah.
Maybe I'm confused. The adaptive lower bound is higher than the non-adaptive lower bound?
Yeah, because no, it's it's log n.
What's log? Sorry.
Yeah. Any more questions? Great. So I should also mention that the question of computing median has been studied in other models like time-space trade-offs, streaming algorithms. It was also considered in the context of data structures, in the comparison model, where they had very tight upper and lower bounds. Good. So I actually have about 15 minutes. And I'll be able to show you the complete proof of one of the theorems, and so we'll do that. So I just want to okay. So let's start by I'll describe what the sunflower lemma is. I'll remind everyone of what the sunflower lemma is, as this will be the key technical tool that we use. So what this says is if you have a sequence of n sets where each set is of size t, then if you have the number of sets to be large enough, roughly p to the t, then you can always find a sunflower among them. Okay. By a sunflower, I mean you have a subset of this collection where pairwise intersections are always the same. Okay. And the thing to note here is n is roughly p to the t, where t is the size of each set, and you'll actually be able to find a sunflower with p petals. Okay, or yeah. Good. Great. So also I should say that it's not something new. Sunflowers have been used in complexity a lot. For instance, in the case of monotone circular lower bounds. Also, in fact, they have also been used in the context of data structure lower bounds in both dynamic and static data structure lower bounds in the bit probe model, and we also apply it in a very similar way that it was used before. Okay. Good. So the goal for the rest of the talk is to prove the following theorem, where you're given a data structure where you know that where ti is the time to perform the insertions and tm is the time for the median, and both of them are non-adaptive, and you want to show a lower bound of log n or log n on these operations. Okay, so this will be the goal for the rest of the talk. I can go slow. Please ask me questions if something is not clear. Okay, perfect. Great. So the outline of the proof is going to be as follows. First, we'll come up with a sequence of sets, of n sets, where n was the universe that we are working with, and the ith set is nothing but the set of all cells that are accessed while inserting the number I, or that's used while computing the median. Okay. And then we'll use these n sets to find a sunflower with roughly p petals, where p would be roughly n to the 1 over t, where t is the time for these computations. Okay. And then what we'll claim is you can you just look at the contents of the core to encode a large random subset. Okay, so that will be the outline of how the argument is going to proceed.
And the idea is that this subset is too large to be encoded so efficiently?
Yes, exactly. Yeah. Good. Great. So, okay. So as before, let me remind what the ith set was. It was the set of all cells that was accessed while inserting the element I, or the number I, or computing the median. Okay. So now we actually get a sunflower with p sets. Without loss of generality, you can assume that these correspond to the cells that was are like these are indexed by 1 through p, and not worry about because you care only about the median computation. Like the rank of all these elements are going to be preserved in this operation. Okay. Sorry, just to repeat, what I meant to say was, like, you have x1 through xn, and you'll find p sets in this collection which are xi1 through xip that form a sunflower. All I'm saying is where i1 is less than i2 is less than ip, just think of it as 1 through p and not worry about the indexing. Okay, great. So now pick set S that's an uniformly random subset of the middle 1/3 elements. That's exactly between like p over 3 and 2p over 3. And now use the data structure to perform the insertions. Insert these numbers. And now you will actually have a bunch of cells that are accessed. And here, like, when I've shaded a petal, it means that that particular element was inserted, and some of the cells associated with it were like actually modified. Okay, good. Now the claim is that the contents of the core encode the set that you just inserted. So this is the key claim. Does anyone have ideas or like? Okay, so let me tell you the proof. It's not too hard. So we are going to use the sunflower structure very crucially here. So the first key claim here is if you actually look at any number that's not in the middle 1/3 range, if you would like to insert this number now, you only need access to the core. For instance, if you were to insert this number 2p over 3 plus 1, you only need access to the core because you know that all the cells that it accesses that are outside the core were never touched by the insertions that were performed earlier. Okay, so to simulate these operations, you just need to know what the core is. Okay, this is very powerful because now, there's one more fact that we need to use. You know that all these sets xi's contained all the cells that were used to compute the median. So by just looking at the core, you should be able to also compute the median. So now you repeatedly insert elements that are like in the that are not in the middle 1/3 range, and keep computing the median, and this will help you recover the complete set. What I'm saying is, like, you just need the core to compute the median of the set S, and now you add an element that's like more than 2p over 3, and this will give you the element that's like 1 away from the median in rank. That's to the right of the median when you sort the elements of S, and you insert one more element to get the element greater than that, and so on. So this way you will be able to recover all the elements of S that are greater than the median, and now you can always perform or like keep adding numbers that are less than p over 3 to like recover everything that's yeah.
And the non-adaptivity comes in because you're now only performing the operations that are like in your sunflower, not the other.
Right, exactly. So like for the set xi to be well defined, you need non-adaptivity. Like to compute the median, you know that you're only going to always access a fixed number of cells, and they're not going to depend on the current contents. So they have to be present inside the core. That's where non-adaptivity is used, and that's also used in like for the insertions cases. Okay. And now, so this is good enough because yeah, the entropy of the set that you inserted was like P over 3, and the number of elements or like the number of bits that you require to actually encode the core is, or like write down the core is W times Ti plus Tm, where W is the word length, and each set is of size at most Ti plus Tm. So you know, this is a standard entropy argument, and this should tell you that Ti plus Tm should be at least P over W, and P was roughly n to the power 1 over Ti plus Tm. So this should tell you that Ti plus Tm is log n or log n.
Yeah. So one side. So why again? Why do inserts only touch the core?
No. So inserts. Okay. So
Outside this range.
it could touch something outside as well. But when you're inserting an element that is not in the middle 1/3 range, or when you're inserting an element that's not inserted before, you only need to know the core, because no other cell outside the core was ever touched, and that is like using the sunflower structure. Like yeah, when inserting this particular element, like the elements that are like outside the core were never touched before, because they are like disjoint from every other. Okay. So hopefully, like that was clear. Or any more questions? Okay, perfect. So this gives you the log n or log n bound. So I actually have a few more minutes, so I'm going to quickly tell you how to, you know, get the stronger bound. So when you only assume that the insertions are non-adaptive, in this case the median computations can be adaptive, but you still get a stronger lower bound where like the time to compute the median is at least n to the 1 over time for insertions. Okay. So here we start like before, where you actually define the ith set to be the set of all cells that were accessed while inserting the number I, and you'll again find sunflower among them. And now instead of so now what you'll argue is you'll actually say that the median computation, since the insertions were non-adaptive, it will help you not just compute the median, but it will also help you compute the kth smallest element in the set. Okay, and then we know how to prove lower bounds against kth smallest queries using the chronogram approach, and then we'll use that. So again, let me quickly tell you what the reduction is. So you'll again only look at a set, or you pick a random subset of the middle 1/3 elements, and then the claim is once you know the core, so you insert the set, and once you know the core and size of the set, you can always find the kth smallest element in time that is the same as time to compute the median. This is because, as before, you know that you insert the set S, and a bunch of cells get you know, or like petals get shaded. Now if you would like to insert any element that is not in the middle 1/3 range, you just need to know the core. So you can always like move the median to the kth smallest, because you know the size of the set, and just asking for the median or computing the median using the data structure is going to recover the kth smallest element free. Yeah. Anything outside is you get it for free by just knowing the core, and yeah, you can now compute the median to recover any kth smallest once you know the size of the set.
But it could be that when you compute the median, you access things that are not in the core.
Right. Good.
So you need to know things that are outside the core.
Yes, that is correct. So now, yeah, the argument is not complete. So this says that the time to find the kth smallest is the same as the time to compute the median. Mm-hmm. So I'm not claiming that it reads the core, but it's the same. Mm-hmm. So you can use ideas from or like the chronogram approach of Fredman-Sachs, and along with the reduction from Petrasco and Thorup, where they show that like to compute the kth smallest element, even in the adaptive case, you have a log n lower bound. So plugging that in would give you a lower bound of Ti times, or like time for insertions times the product of time for median is at least log n or log n. But then we actually claim something stronger. This is because you can actually open up the proof of the chronogram approach and then use the sunflower structure to improve it. and you get something stronger. So instead of just the products being at least log n, you would like get a polynomial trade-off here. Yeah, the key idea is in like reducing it to kth smallest, or like using the median to compute the kth smallest. Okay. And some pretty pictures. Maybe I'll skip this. Yeah. So I'll just conclude with an open problem where, like, as mentioned before, like in case of like worst case times, can you show a log n over some poly in log or some smaller factors on the when both insertions and median computations are adaptive. Okay, and here like even in the worst case, like even like super constant seems to be open. And like nothing special about median, you can also think of like minimum or maximum, but you'll have to allow deletions, otherwise the problem is very easy. Yeah. Perfect, thank you.
Any questions? Oh, did you consider kind of hybrid models with some adaptivity but not full adaptivity?
Yeah, so we have some results where like insertions are adaptive, but in the case of the median lower bound, like the queries are like non-adaptive. Sorry, for predecessors, queries are non-adaptive, but updates are adaptive. But in the case of median, updates are non-adaptive, but the queries are adaptive.
All right. I was thinking more like you have to send off batches of memory accesses at a time.
No, actually, yeah, I cannot. No, we didn't consider that, yeah. Okay. And I cannot think of anything on the top of my head, yeah.
More questions? This brings